Great way to spend a Friday night. But in any case, I opened it back up. I hope nobody's going to be doing it at 11:59 p.m. tonight. So we were talking about uniform circular motion the last day and a half of class, which seems forever ago now. And of course, one of the big examples of that is celestial motion. You know, a lot of celestial bodies, moon around Earth, Earth around sun, other planets around sun. They're not exactly circular orbits, but they're almost circular. And that means they're pretty much uniform too. So that's a great example of uniform circular motion. In order to understand that, we need to know a little bit more about gravity than we know right now. And so, you know, because this is a Gen Ed course, let's just do a little brief historical perspective of our place in the universe before we jump into Newton, which is a fairly modern point of view by big historical standards. Okay, so let's do slideshow. Okay, so just to kind of set the stage of where we're going, just for like a 10-minute discussion of kind of like the history of things and how we found out some things before the modern point of view, before we talk about in detail Newton's theory of gravity, which we'll spend some time on. How do we find out about our place in the universe? So we're going to talk about things from at 4 different levels. First off, the kind of ancient view that the Earth is flat and the Earth is the center of the universe, and why that makes sense from the point of view of people who lived on Earth a long time ago. And then the evidence that led to the idea that the Earth is a sphere, but still at the center of the universe. Then to the idea why it simplifies things to think of the sun as the center of the universe and have things, you know, there's the planets and stars and things going around the sun. And then finally, how we were relieved of that kind of point of view and sort of, you know, think now of the universe as not having a particular center. No one's at the center of the universe. There are lots of different centers within the universe. So let's first talk about why flat Earth models, you know, you hear about this in the news nowadays, people believing in flat Earth models, but, you know, in ancient times, it made perfect sense. I mean, first of all, when you looked around, of course, there were hills and valleys and gullies and things like that. But more or less on average, if you got to a place where you could see far away, it looked like the Earth is pretty much flat. So that kind of makes sense from an intuitive point of view. It shouldn't be surprising. The second aspect of this model is, well, you know, the ancients not having indoor lighting and things like that, spend a lot of time outside staring at the stars. And one of the things you notice very quickly when you go outside and look at the stars, we don't do too much anymore, is that they're moving as time goes on, right? If you watch the position of the stars relative to objects on the horizon, you see them going around in circles. And if you ever notice, you know, looking at a distant mountain range or something like that, a lot of times it's hard to tell because your brain does a lot of interpreting. But, you know, when I look at something close by in the room here, I get a really 3D effect. In other words, I can tell that tripod is a lot closer than the back of the room. But if you look at distant mountain ranges, they actually do look rather flat, and it's hard to judge the distance of things when they're far away because I'm using my eyes and the angle that my eyes bend in. When things are far away, they're basically pointing straight ahead. Even if one thing is millions of miles in front of the other, they both look the same distance to me in terms of the angle of my eyes. So, you know, putting those all together, the ancient model that people accepted was a flat Earth model where people think of, you know, at least in the simplest case, the Earth as some sort of flat disk. And what are the stars? Well, the stars look like they're all sort of the same distance away. So they're on this dome that surrounds the disk of the Earth. It was sort of a mystery or an object of speculation of what happened when you got to the edge of the disk. But this dome was called the firmament. So the firmament held the stars in it. The firmament rotated around as time went on, and that's why you saw the stars rotating around the sky. So we were surrounded by this big dome. Now, as people started paying more and more attention to the motion of those stars and what stars you see at which time of year, there were some problems associated with it. And that's what led to the idea that Earth is not flat anymore. And Aristotle was a big player in this. He noticed, well, these are the two biggest things that he pointed out. One is that, in talking with people that traveled south quite a distance from Greece, into Africa and south down there, people would report seeing constellations that you couldn't see ever when you were in the northern hemisphere. So new stars appeared. And if you look at this, sort of woodcut drawing of the firmament of the flat Earth, no matter where you are on Earth, you should be seeing the same stars, right? Everybody has access to that same kind of half dome of stars at every time. If you never see a star over here, you shouldn't see it no matter where else you walk on Earth. So that doesn't seem to make sense. And they rose different distances above the horizon too. That's another piece of evidence. The second big thing that Aristotle pointed to was that when there was a lunar eclipse, that means the Earth gets in between the sun and the moon. And so when we look at the moon, we see the shadow of the Earth on it. And Aristotle noticed that that shadow was always circular. And he thought, well, that's kind of strange, because if you have a disk and you shine a light on it, unless the light's exactly perpendicular to the disk at all times, you're going to see an elliptical shadow in general. But we always saw in every lunar eclipse a perfectly circular shadow. And so he realized that, spheres cast circular shadows no matter what, whereas with a disk, it seems like somewhat of a coincidence. And so Ptolemy and Aristotle sort of developed this model of, slight improvement that it's still rather similar to the flat Earth model, except Earth is now a sphere. And instead of having a dome going over the sphere that's the flat disk, we have a dome surrounding the entire spherical Earth. So there's still a firmament kind of thing in this model. The stars are still attached to the firmament and they're rotating around. So we're just sitting at rest on this Earth, but the stars are moving around. The planets require a little bit more explanation, but we'll get to that in a minute. Now, as soon as you say the Earth is a sphere, the question is, how big is the sphere? And that was a question that could actually be addressed by the ancients. Here's a famous experiment done by Eratosthenes, 200 BC. And it's rather clever. I mean, I wish I could have been the person to think of this in ancient days. It was well known. Okay, so there was this obelisk in Alexandria that was erected exactly perpendicular to the Earth. That was rather tall, right? So just a pointed monument. And there was a very deep well in Syene that was south of there. And I can't remember where Syene is. Maybe it's somewhere. It's still in northern Africa, I believe, but quite a distance south on the Earth. And it was known in Syene that on a certain day of the year, at high noon, the sun would shine exactly down to the bottom of the well, and there wouldn't be a shadow from either side of the well. In other words, it would illuminate the entire bottom of the well of a cylindrical hole in the ground. And it was also known that on that same day of the year, people start talking to their friends who travel down south. On that same day of the year, the obelisk in Alexandria cast shadow to one side. And Eratosthenes got to thinking, something about, if you remember your old, you have a circle and you circle of radius r, and you cut out a little pie-shaped piece of angle theta, and you call this arc length, usually in math classes, people call that S. There's this relationship that maybe some of you have learned before that tells you how to calculate the arc length in terms of the radius and the angle. They have to measure the angle of radians, but you can convert one into the other. So what Eratosthenes realized is that the Earth is a sphere. And at this point, by the time he was doing this, it was accepted because of the Aristotle's observations, and people wanted to believe it because a sphere is the most perfect shape, and that held a lot of weight with the Greeks back in those days. That things were supposed to be perfect, and spheres were perfect. So if the Earth is a sphere, if we have a certain distance on the sphere between these two objects, the angle, you know, this one casts no shadow here, then the angle that's cast by this obelisk, in other words, that little angle in there, or this angle up here, it's labeled as alpha on this diagram, is actually the same as the angle subtended by this distance on Earth. And so we can measure that angle from the obelisk. If we can only measure this distance on Earth, and they could measure it. They had a caravan. They had different units. You know, they didn't use miles or kilometers back then. They called it stadia. But they measured that distance in stadia by having camels just sort of march it out and see how far they had to go. And using that distance and this angle, you could figure out what the radius of the Earth was. And Eratosthenes got very close to the accepted value that way. So that's amazing. Way back then that people knew how big this spherical Earth was, where it's not too long before that. Everyone thought it was just a flat disk. Okay, so why switch from an Earth-centered model to a Sun-centered model? Well, part of the problem with the Earth-centered models is that the motion of the stars are perfectly normal, right? They're on a big sphere and they're sort of rotating around very regularly. But if you look at the planets are actually doing really crazy motions. And Copernicus realized that if you put the sun at the center, the motion of the planets would be greatly simplified relative to the sun, relative to how they move around the Earth. They're not really moving around the Earth, and they're not modern. So the Copernican model has the sun at the center, the planets in various perfect circular orbits around there, and at the very outside, again, still here's our firmament. There's still a fixed sphere of stars around the whole thing that was rotating now around the sun, not around the Earth anymore, right? But still in this model. So in Copernicus' model, it still is perfect circles that everything's moving in. Of course, we now know these planets don't move in perfect circles around the sun, and so there were discrepancies with that model. And Kepler's improvement on that was to say, well, I'm going to make 3 laws, and one of them is that the planets don't necessarily go along circles, but they go on ellipses. Ellipses can be circles, but they can also be slightly different shapes of circles. So let's just briefly talk about Kepler's laws, because I think this was in the reading. We're not going to use them too much, although sometimes we'll find that we can use Newton's law of gravity to derive Kepler's laws, but one of the laws actually greatly simplifies some calculations, so you'll see it's occasionally useful. Okay, Kepler's first law says that the orbit of each planet around the sun is an ellipse with the sun at one focus of the ellipse. Okay, so what does an ellipse mean, and what is the focus? What's the focus of an ellipse? And we just go to a little diagram. Here's an easy way you can construct with a piece of string and a pencil an ellipse. You just put down 2 tacks on a piece of paper, a fixed length circle of string, and you keep it taut and pull all the way around, keeping it taut between, making a triangle all the way around. That'll draw an ellipse. And where these 2 tacks are called the foci of the ellipse. Each one is a focus of the ellipse. So the claim is that in this first law, the sun is at one of those locations that the tack would be at. Now, most of the planetary orbits aren't too elliptical. If you look at them, in a diagram, sort of looking down from the heavens, you'll find that they're mostly circular, but they are a little bit elliptical, and some planets are more elliptical orbits than others. The second law Kepler gave was something about the speed of the planets as they moved around. It turns out they slow down when they're far away from the sun, and they speed up when they're close to the sun. So his law was phrased in terms of areas. You could say, in a certain amount of time, we would say this planet 1 that's on this sort of purple orbit here sweeps out this arc length there on the ellipse. And we would also say it sweeps out this area A1, which isn't really a piece of pizza shape, but it's part of an ellipse kind of analogy to pizza. At a later time, when it's farther away from the sun, it sweeps out in a certain period of time this area A2. And the claim is, in a given amount of time, in 1 month, it sweeps out the same area in any part of the orbit. So that means when it's closer to the sun, there's not as much distance to get to the sun. it has to go a much larger distance along its orbit in that same time as when it's out here, right? Here we have a great distance there. So to get the same area, I don't have to go very far along this direction. That means essentially it's telling us exactly how planets slow down as they get far away from the sun and how much they speed up when they get close to the sun. That was the second law. They're not just on ellipses, but they slow down in a very particular way. The third one tells something about the relationship between the size of the ellipse and the period of the motion. And as you know from the reading, the period means the time it takes. Anytime you have something that's periodic, that means it repeats over and over again, like when this planet goes around on an ellipse. The period is the amount of time for one complete revolution. And usually people denote that by capital T, is the symbol in physics for a period. So if A is, oops, oh, I lost the connection there with this. If A is the semi-major axis length, what does that mean for an ellipse? Well, the major axis for an ellipse is the biggest diameter you can draw across that, that longest distance going through the center of the ellipse. Semi-major axis means half of that. So notice the semi-major axis length, if it were a circle, which is a special kind of ellipse, would just be the radius. So this is like the generalization of a radius for an ellipse. That's what that A is. So you can think if it's a circular planet moving around the sun, this would just be the radius R of the orbit. Kepler is saying that if you take the cube of that semi-major axis length divided by the square of the period, that's the same for every planet that's orbiting the same body. In other words, every planet's orbiting the sun, and so if you get a bigger semi-major axis length, you've got to have a bigger period. So in other words, the planets that are farther away take longer to get around. And this tells exactly how much that time gets long. Okay, you're not going to be tested on Kepler's laws, but it was in the reading, so this connects to it. We can derive these. Some of them are harder than others, but this third one is actually pretty easy to get out of Newton's laws of motion that we'll talk about. His gravitational law plus the second law of motion. Okay, so that's a sun-centered model. And now let's go to the more modern point of view, which starts with Galileo. Galileo was an inventor of telescopes. I mean, sort of a polymath, really good at lots of different things, but he built the best telescopes in the world. So he was observing things that nobody else could see at the time he was alive. Okay. And that means that he could look at things like, for example, one of his famous things he looked at was Jupiter. Stared at Jupiter and he saw something that he reported. In fact, this book or collection of results that he published called Sidereal Messenger contained a lot of things that nobody knew about. So it was really revolutionary at the time. Views of the surface of the moon that nobody knew about before, but studying Jupiter was one of the main things. That's what I'm going to talk about here. Amazing, this is a translation. I don't know if it was in Italian or in Latin, but this is if you read it, it's like nobody makes subtitles like this before. The Sidereal Messenger, unfolding great and marvelous sights and proposing them to the attention of everyone, but especially philosophers and astronomers, being such as have been observed by Galileo Galilei, a gentleman of Florence, professor of mathematics at the University of Padua, with the aid of a telescope lately invented by him, respecting the moon's surface, an innumerable number of fixed stars, the Milky Way, the nebulous stars, etc., etc., etc. Seems like in old days people used to make big subtitles or title pages like that. But here's something when he's observing Jupiter. Let's just read a little bit of this because it's kind of fun to see him figuring something out as he's taking notes. I was viewing the constellations of the heavens through a telescope. The planet Jupiter presented itself to my view, and as I had prepared for myself a very excellent instrument, I noticed a circumstance which I had never been able to notice before, owing to want of power in my other telescope. Namely, that three little stars, small but very bright, were near the planet. And although I believe them to be among the number of fixed stars, they made me somewhat wonder because they seemed to be arranged exactly in a straight line, parallel to the ecliptic. The ecliptic is, if you watch the sun going around the earth from our point of view, is that, line or circle that the sun is going around in, and to be brighter than the rest of the stars. equal to them in magnitude. The position of them with reference to one another and to Jupiter was as follows. And so then he has some drawings in his manuscript. And Galileo wrote great manuscripts. It was filled with little pictures he would draw in the middle of the words everywhere. So it's really well illustrated. So here he is. Here's Jupiter. He's drawing, he's got the date over here. Here's Jupiter, the big circle. So he's not just seeing it as a dot. He's seeing, actually the cross section of Jupiter. And here on one night, he's seeing two of these fixed stars to one side. Here's the next night. Now there's three of them that he can see, all arranged in a line. And he observes night after night after night, unless there's clouds out that night. Of course, you miss your night of data if it's a cloudy night, but at any night he could take the data. This is what he's seeing, and they're always staying in the same line, but moving. The fixed stars, of course, don't move with respect to each other. They're all just rotating around the Earth. At least that's the way people were thinking of it at the time, right? The fixed stars are just moving together. They don't move relative to each other. So Galileo, of course, understands that what he's looking at is moons going around Jupiter or something orbiting Jupiter, except that he's looking at it edge on like this, and he's seeing those moons go around and appear on different sides of the planet. Sometimes they're obscured by Jupiter, so you can't see them because they're behind, or maybe they're in front of Jupiter and they're too hard to see with this telescope, so they occasionally disappear. And that's revolutionary because that means that there's no, in some sense, Jupiter is its own center of some sort of motion, the same way the sun is a center. And this loosens the idea that there has to be some special center at the middle of everything. Maybe these other stars are just like suns and everything's orbiting around everything. So that's the beginning of the modern view. There was someone named Giordano Bruno who proposed a cosmology with no firmament, still kind of revolutionary, that there wasn't some fixed stars that were just really far away and fixed in space and rotating all together. An infinite universe in which all the stars are actually suns with their own planetary systems. Now, this was sort of more, not based on data necessarily, but it was a fanciful vision that really was visionary of the way we think of things now. And after Galileo's observations, it's sort of harder to go along with the Aristotelian kind of view that everything's perfect in the heavens and there's something right at the center, and maybe the center has to be us because we're the most important beings in the universe. Rather, everything's sort of its own center. Okay, so Newton begins to think of space. We haven't talked really at all about space, but Newton thinks of space as kind of a container that's the same everywhere. We're not talking about the air in the room. We're talking about the places you can be in the universe. And he thought it just kept on going and going. And being here is just as good as being over here. So it's sort of a featureless container. And there's a gravitational force law that determines a force between all bodies in the universe. And along with F equals ma, is F net equals ma, if you know the gravitational force between things, that tells us how they're going to move later on in time. And I put this on our syllabus, but that was really revolutionary, to connect the idea of how things fall here on Earth to what people had observed for so long of the motion of heavenly bodies, that those are part of the same kind of dynamics, the same motion. This is attracted to the Earth because it's gravitationally attracted. Now, that connects those two things that were sort of thought of different subjects of study for so long. Okay, so we are, going to use our uniform circular motion kinds of ideas if we consider the Earth as fixed. It's kind of hard to know. Is the Earth fixed or is the Earth moving through space? Well, you can ride along with it and pretend it's kind of fixed as long as you don't do it for too long, and as long as it's not going, you don't do it for a good fraction of the year. The moon's orbit is approximately uniform circular motion. And the same is true for Earth's orbit around the sun. And so we're going to apply that to gravity. Gravity is going to be the force that keeps them moving in uniform circular motion, or almost uniform circular motion. And so our job now is to describe Newton's theory of gravity, which really revolutionized and allowed him to compute a lot of stuff about the motion of heavenly bodies. It's called universal gravitation because everything exerts a gravitational force on everything else. That means each of you in the room is attracted to each other person in the room. You're not just attracted to the Earth, but every bit of mass is attracted to every other bit of mass. It's just that the force is really puny for most human scale bits of mass. It's hard to measure the gravitational force between, two objects here in the room. We'll find out why that is in just a second. Newton's force law says that, of course, if this mass has a force exerted on it by this mass over here, maybe this is Earth, maybe this is the Moon, right? The forces exerted on each one have to be equal and opposite. That's Newton's third law. We already know that, right? They've got to be exactly equal and opposite, that each one exerts on each other. So there's only one force magnitude to talk about. The magnitude of that force is always toward the other center of the other sphere. It's more complicated if the thing is not a sphere, but most of the time we'll be talking about planets and things like that, so there's a definite center of the sphere. R here is the distance between the centers of the two spheres, okay? And so Newton's force law, universal gravitational law, says there's a constant capital G times the product of the two masses that are pulling on each other, divided by the square of the distance between the centers of the two masses. And that constant is called capital G, the universal gravitational constant. It's not little g. And its value in SI units is 6.67 times 10 to the minus 11. And that explains why gravity is so weak for normal objects, right? If I take a kilogram object, separate them by a meter, that means in SI units, M1 is 1, M2 is 1, R is 1, then the force strength between them would be 6.67 times 10 to the minus 11 newtons. So 2 kilograms separated by a meter don't pull on each other very hard. That's one of the reasons that small constant tells us why we don't notice gravitation at our everyday scale. The force that dominates our world here is the electric and electromagnetic forces, but mostly electrical forces, right? The force between my foot and the floor ultimately is electrical forces, right? It's electrons repelling electrons that are at the outer, bits of molecules. They're coming close. All of a sudden, I'm not too much extra charge here, so they don't repel each other. But all of a sudden, the electrons are a lot closer than the protons when they get close to each other, and so it feels like there's a solid surface there. So electrical forces actually have the same force law, except there's a different constant there, and this is the charge of object 1 and the charge on object 2. And this constant that goes out in front is usually called little k in physics. It's about 10 to the 10 in SI units. So it's huge. Now, you might wonder, how does gravity ever get to overcome electric forces? And that's comes down to the fact that there are 2 charges, but only one kind of mass, right? If I have 2 charges, that means the electrons and the protons will more or less balance each other out, right? And so if I get a big object, it'll probably be just about neutral. Another one over here will probably be just about neutral. If it's not neutral, it'll start attracting charges of the other side until it's neutral. And then there's no force left on each other. But for mass, as an object gets bigger and bigger, it has no choice but to get more and more mass. And so things just build up. And when you start getting planet-sized things, the gravitational force gets rather sizable. When you get to stars, it gets really big, whereas the electric forces between planets are almost zero because the Earth is almost completely neutral. There's not that much excess charge at any one time. Okay, and the units, of course, how would I figure out what these units are if I didn't give that to you? Kind of an ugly mess of units. There's no shorthand for that, but the units for capital G, how would I figure that out from the law there? Yeah, you rearrange, you solve for G, right? And we know the units of everything else. If I solve for G, I've got a meter squared that goes up there next to a newtons, and I've got to divide by kilogram squared if I solve for G equals. So you can figure out what those units are. I never remember what they are off the top of my head, but I know if I just look at Newton's law of gravitation, I'll be able to figure it out right away for SI units. Okay, let's just do a quick calculation here. With what force does Earth pull on moon? I know it sounds a little bit strange to people. Nowadays, astronomers tend to capitalize these and they use them like proper names. So, people don't say the sun and the moon. They say, how hard does sun pull on moon? Just like we say Earth, as the proper name. So I'm trying to stick with that here, even though it still sounds a little bit strange to me. So I'm just going to plug into here. And some of these things we need to plug into here are in the back of your book. So here's some things I looked up in the back of the book. All right, capital G is down here, 6.67 times 10 to the minus 11, that puny number. The two masses are the Earth mass and the moon mass, 10 to the 24 and 10 to the 22 kilograms about. And the distance from the center of Earth to the center of the moon, you measure from surface to surface, it's not that much different, but is 0.385 times 10 to the 9 meters. So pretty big distance. It's hard to know how that's going to shake out in here, but let's throw them in there and see how big the force is. So I just multiply them all together. You've got to be good at this point in the course of knowing how to do exponential notation, scientific notation in your calculator, right? Most calculators have that button, at least on my TI calculator, it's labeled as EE. So if I want to do 9 times 10 to the 11, I can do a shortcut. I don't have to do 9 times 10 to the power 11 because it's just too clunky. You just do 9, at least in the TI calculators, looks like this. You hit the EE button, and that means times 10 to the power. That's what it's shorthand for. And then you hit 11, and then you hit enter. And you'll see a 9 with 11 zeros after it. Right? Just saves you a lot of work there. So get used to that exponential notation on your calculator. Okay, so that's just, it's a big number, 2 times 10 to the 20 newtons. Well, what do you expect? It's the Earth and the moon. There's got to be a big force pulling the moon in a circle. It's a massive moon. Okay, let's just try a worksheet to practice with this. This touches on both. So for those of you who are on Zoom, this is posted on the website. Is it under today's date or was it under Monday's date? One or the other. I might have posted it for Monday's date, but maybe it's today. We're just going to do problem 1 on here, which connects up with some of our circular motion stuff that we were doing before. So someone's in the space station, which is a given distance away from the center of Earth. Now, I should warn you about homework problems here. Normally, when we say how far something is up above the Earth, we measure from the surface of Earth. And so you got to remember that when you're doing these problems, if you're using Newton's law of gravitation, you always have to measure distances to the center of a large spherical body. Now here I happen to give you the distance to the center, but not everyone is going to be so nice about that. A lot of times people will tell you the altitude, and that means you've got to add the radius of the Earth on it before you can consider it that R in the law. What's the magnitude of the force on the person who's in this circular orbit? What's the magnitude of the acceleration? What's the speed of the person? If the person stands on a scale, what's the scale reading? And how long does it take the person to orbit once? Let's just do A and B. Why don't you spend a couple of minutes working on A and B there? And maybe we can hit C, D, and E later on. Oh, I'm sorry, I forgot to switch my microphone over. I think my wireless microphone. Hopefully that's better for those of you on Zoom.
part of this is just to force you to do that exponential notation in your calculator and make sure you're reasonably good with it, where you're going to start to see a lot of big numbers and small numbers. And so you got to figure out your calculator's scientific notation. Did I put, oh, I did put, okay, it's not on my solution one. I did put the mass of Earth up in the upper left corner. You'll need that here. So here's our calculation for A that we're doing, and it's, just to check that you're plugging in the right way. This is approximately 577.6 newtons. Now, this person isn't that far away from the surface of the Earth. If you look, it's 6.7 times 10 to the 6 meters is the distance to the person from the center of the Earth. The radius of the Earth is 6.37 times 10 to the 6th. So the person's going to have slightly less weight out there because they're a little bit farther away. So if we compare this to mg, you could calculate their m, 65 times 9.8. You'll get a number that's a little bit greater. They weigh a little bit less. I mean, we really would say their weight is less out there because they're farther away from the Earth. Or equivalently, little g is a little bit smaller when you're on the space station than it is at the surface of Earth. Okay, any questions on that? Just to kind of check. And then what's the magnitude of the acceleration? Well, I could, anytime I want to find acceleration, a lot of times I'm looking at Newton's second law. Here's Earth. Here is the person of mass 65 kilograms. They're attracted to the center of the Earth, and we just found that was a 577.6 Newton force. And I don't see any other forces that's acting on, no normal forces, no friction out there, whatever. They're just orbiting around. Presumably they're floating in the middle of the space station or something like that. And so my free body diagram is pretty simple. I'm just going to, as usual, take my positive axis going towards the center of the circle that this person is traveling on around Earth. Okay, and if I do F net equals ma, the sum of the force x components equals max, we're after that ax. That's going to be the magnitude of the acceleration. So this is 577.6 equals 65 kilograms times ax. Ax is 8.89 meters per second squared. Okay, so little g is about 10 here. They're in, technically you could say they're in free fall around the Earth. When something's in orbit around something and there's no air resistance, you're outside the atmosphere here, they're technically falling toward the Earth. It's just that they happen to be moving sideways, and every time they fall, the Earth kind of curves out of the way at the same rate, and they happen to be going in a perfect circle there. Okay, we'll talk about C, D, and E maybe later on if we get there today. Otherwise, Monday. Questions on those? Good, let's go back to the slides now. Okay, now I've left out a lot of details that if you're on top of things, you might say, now, wait a minute. How do people know how did Newton know how to get this law? I can calculate the force between objects if I know their masses and separations, but we just looked up in the back of the book what the Earth's mass is. How do I figure out what the Earth's mass is? It's not like you can weigh it on a digital scale. It's not like you can grab it and shake it and see how much inertia it has, right? Our usual way we measure masses on Earth are one of those two well, we usually don't use the inertial way, but if you're out in outer space, you find the mass is length by shaking it back and forth and seeing how hard it is to accelerate. Neither of those are going to work for the Earth just because it's so big. So how are we going to obtain its mass? The answer is, and this is the same for every other astronomical object, where do we get a value for the mass of Jupiter? Galileo, if he knew the distances he was seeing in his telescope, could have figured out the mass of Jupiter by observing it. What you do is just watch something orbit it. And we don't need to put up satellites. We already have a satellite. It's called Moon. And so let's watch Moon go around Earth and see how we can back out the mass of Earth from that. We really only have one choice, and that is we'll draw a free body diagram for Moon orbiting Earth. There's only one force on it. It's the Earth's gravitational pull on it. We know a formula for that. And we're going to do F net equals ma. And we'll have to work on it a little bit, but let's start there. So here's Moon at a certain point. Force is directly towards the center of Earth. That's my free body diagram. I always choose the same axis going towards the center of the circle that it's moving on. Okay, and let's do F net x equals max. On the left-hand side, there's only one force. Comes in with a plus sign, and we've got our universal gravitational force there. That's Newton's gravitational force. That's equal to the mass of the thing in the free body diagram, that's mass of Moon, times the acceleration x component, and that's v squared over r, because x goes towards the center of the circle. So that's the speed of the Moon squared divided by the distance. So this REM is supposed to be the distance from the Earth to Moon, right? The distance from center to center. There. Okay, now we know maybe, well, so the first thing, there are some fortuitous cancellations here, right? If you look on both sides, there is, I've lost control of my pointer again. There is a mass of Moon on both sides. That's kind of nice, because in order to measure the mass of Earth, we don't want to also have to know the mass of the Moon, or we're pretty much screwed there, right? Because we don't know the mass of the Moon either. And also, I could have, I don't know why I didn't do this down here. We could have canceled one factor of the distance from Earth to Moon in the denominator. And so I've canceled out the Moon's mass there. Now I don't know the speed of the Moon, but we're going to translate that into some information we know. And that's using my old distance over time trick. That is, if we know how long it takes the Moon to do one complete revolution around Earth, and we can know that just by watching the Moon, right? It takes about 27 days for the Moon to go around one time. So 27 days, 24 hours a day, 60 minutes an hour, 60 seconds a minute. That's how many seconds it takes the Moon to go around Earth once. And the distance it goes is 2 pi times the radius of the circle that it's on, the distance from Earth to Moon. So I'm putting all that junk in the square there. And what I'm going to do now is, there's some cancellations that take place, but I'm just going to solve for the mass of Earth, right? You have to think, well, okay, I've also got to know the distance between Earth and Moon. And, the modern way we do that is, when the astronauts were on the Moon, they left something called a corner reflector on there. And the corner reflector is this amazing, it's just 3 mirrors at right angles to each other. And if you shine a light at it, no matter where you shine the light from, it bounces a beam exactly back in the same direction it came from. So what we do from Earth is we shine a laser beam towards that corner reflector. It bounces off of it and it comes back. And since we know the speed of light, we know the time, we can measure the time it takes to go there and back, and we know the speed of light, so we can back out the distance it is, the distance to go there and back. So you have to work a little bit harder in days before people were on the Moon, but still, that's at least reasonable to see how we might get the distance from the Earth to the Moon. We know how we can do it nowadays. Backing that out, you get the mass of the Earth is 6.2 times 10 to the 24 kilograms. So that's pretty close to the value that is on your sheet here, right? Mass of the Earth, 5.97 times 10 to the 24 kilograms is on your sheet. So it's not too bad, right? I mean, this is a pretty crude approximation. It's not a perfectly circular orbit and so on. you know, I've made some approximations in there. The period's not exactly 27 days and so on, but that's how you get the mass of Jupiter. You watch Jupiter's moons go around it, see how long it takes for one complete orbit. And if you can figure out the radius of the orbit, then you're pretty much good to find the mass of that astronomical object. Okay, there's still a little bit of a cheat here. That's better, right? But in order for me to figure out the mass of Earth, I already assumed I knew what capital G was. And the question that Newton actually didn't know the answer to is, what is capital G? He knew it was a constant. It was proportional to the product of the masses divided by the square of the distance. He didn't know what that constant of proportionality was. And so in order to figure out what the mass of Earth is, you need to know what capital G is. And there's no way around it. In order to figure out what capital G is, you have to be able to measure the force between two objects that you definitely already know the mass of. That means two objects that you have sitting in the lab, right? So I have to have two objects and very precisely measure the force between them. It's a puny force, so it wasn't something that was easy to do. But Cavendish is the one who did it. He actually took lead spheres, a little lead sphere and then a big lead sphere, put them near each other and measured the force between those two spheres. And knowing the masses exactly, and knowing the distance between the centers exactly, and measuring the force, he could figure out what capital G was. And here's how he did it. This is called the Cavendish balance in his honor. You have a very thin wire hanging from the ceiling, and then a rigid bar that's hanging horizontally suspended. So it's attached to that wire in the center. And on that, you have your two smaller lead masses, okay? And as you know, when you have something connected to a wire, it's pretty easy to twist it. Now, it has a preferred position where it would like to come to rest. But, you know, if you twist the wire a little bit, it hardly resists at all. So it's very sensitive to forces like that. So you put those things on there. You have to make sure there's no wind in the room blowing things around. You let it go. It starts oscillating, and you come back hours later when it's finally settled down and come to an equilibrium position. And then what you do is, after those two have settled down on the bar, you put some huge lead masses right next to them. And what happens is, you back up, you close your airtight container or whatever, so there's no wind in there, and you find that those masses move close to it, and then they go farther away. And you have to wait hours for this to all settle down until it comes to equilibrium. And they actually move a little bit closer. And if you know exactly how hard it is to twist that wire, which is something people can measure, you know, how hard it is to twist the wire, you can back out what the force is, comparing where this was before you put the big lead mass there to how much closer it moves to it when you put the lead mass there. That's called a Cavendish balance. And Cavendish said, I have weighed the Earth because this was what was needed to know the mass of the Earth. No one knew, Newton didn't know what the mass of the Earth was before that. So it was a big deal at the time. Okay, let's do one more thing. Little g, so we keep on going deeper into little g. You know, at one point at the beginning, it was just sort of a miracle that everything accelerated at the same rate near the surface of Earth. And then we showed that that's not surprising given Newton's second law. Now, given Newton's law of gravitation, we can actually calculate why little g is what it is, if you accept Newton's universal law of gravitation, okay? And the way to calculate what little g is in terms of capital G is we're going to calculate the gravitational force of an object at Earth's surface. The old way is just mg. The new way is g m1 m2 over r squared. And that's going to allow us to calculate what what little g is. So let's do that here. Here's Earth. This is the radius of Earth. Here's a little object where, I mean, I'm trying not to draw it too microscopic, but it's got a mass m. And I'm just going to calculate the weight force of that mass m. The old way is m times little g. And the new way is the gravitational force between these two objects is the weight of little m. And Newton tells us that's capital G times the mass of Earth times the mass of the object divided by the distance between their centers. And this thing's so puny, it doesn't really matter what its shape is. Its distance between the centers is the radius of the Earth, right? Radius of the Earth is the distance from this one center to this one center. So, and Newton tells us to square that. And the nice thing is that little m cancels out, and that tells us that little g is, well, I can calculate it. And, of course, little g depends precisely on what's underneath you and how high up you are above sea level at that position. So it can vary a little bit. This is just pretending everything is a perfect sphere. But once you've done that, once you've done that calculation and the cancellation and found out what little g is on Earth, you can calculate what little g is in other places. In other words, just substitute, something at the surface of the moon. I would put in the mass of the moon there and the radius of the moon, and I could find out what little g is on the surface of the moon if I knew those quantities. And in fact, I could find out what little g is a certain distance above Earth. And so in Newton's theory, we think of little g, and we think of it as a vector that has magnitude of little g, and its direction points in the direction of the gravitational force at that point in space, is a function of position in space. So, kind of the more modern point of view is that little g varies as you go around. It has a certain value when you're close to Earth. As you get farther away, it gets smaller and smaller, but it always points toward Earth. And I think that's where I want to stop for today. We'll do some more practice with this on Monday. I have for Monday's reading chapter 6, and I think that's right. I think what we have left in gravitation will take about a half a period on Monday. So you should be reading those first sections of chapter 6